Welcome back, class. Today I want to talk about vectors, and we're really going to break down in the lab what is the anatomy of a vector. And in fact, oftentimes the first question I'll get from students is why do we need to use vectors? They're so complex. And the reason is because X and Y don't mix in physics. It's really important to isolate the components of motion, of fields, and of forces. So in this case, I always tell my students, Y and X don't mix. And if you need a way to remember it, remember that the reason why you dated someone and how they became your ex are two very different reasons. And while the sum of those two things will make up the total vector of your relationship, they just don't mix. So the first question we're going to address is what are vectors? How do you solve for vector components? And how do you solve for the magnitude of a vector using vector components? And then how do you find the angle of a vector? Please feel free to use the timestamps below to hop to whatever you may need. And they're going to be in chronological order, and they will have a description as well as examples to follow every single one of them. So let's get started. First, let's talk about how to describe a vector. What is it? Well, recall that it's a measurement that has both a magnitude or a size and a direction. A few common vectors are displacement, velocity, acceleration, and force. We have the magnitude or the value that's associated with this measurement, but also there's going to be the direction. And you can do this in many ways using signs, either positive or negative, cardinal directions like north, south, east, and west, or a reference angle. And in fact, today we're really going to be using all three of these so you get a glimpse of where they are useful. So in our first case, let's look at how to describe this vector. We can see that the magnitude of v is going to be 12 meters per second. Now, that part is pretty straightforward, but the next piece is the direction. So in this case, when you're given a reference angle, you can see that it's 30 degrees, but we're not done because in physics, we don't always use the 0 point or the x-axis to define our angle. So because of that, we often will describe it using cardinal directions. So in this case, it's going to be north of east because I start at east and I go up towards north. So in this case, the total vector would be v is equal to 12 meters per second at 30 degrees north of east. In our second case, you can see that the magnitude is going to be 8 meters per second. But in this case, we're actually not starting from the traditional 0 point. We're starting from the negative side of the x-axis, located at 24 degrees south of west, meaning that we move down from west to get to our angle. So our total vector would be v is equal to 8 meters per second at 24 degrees south of west. Now let's talk about how to define vector components. So I want you to recall the definition of the trig identities for sine, cosine, and we'll eventually use tangent. So in this case, we can see that our vector has an x and a y component. And the sum of those two will create our total vector. So the vertical component is going to be sine theta because it's opposite of our reference angle. In comparison, our horizontal component is going to be cosine theta because it's adjacent to our angle. So in this case, we can see that sine theta will give us Vy divided by V. And in order to solve for the y component, we're going to multiply both sides by V. And for the horizontal component, we're going to do the same thing, but with cosine. So cosine of theta will give us Vx divided by V, and Vx is going to be equal to the magnitude of the vector times cosine. Now this is a specific setup that works whenever we have the angle drawn from the x-axis. Let's go ahead and practice it. So first things first, before we get started today, make sure that your calculator is in the correct mode. You want to use degrees, and I know that sometimes in class you may use radians, but in this case you want to use degrees. So for our first example, we're trying to figure out our Vx and Vy. We have the magnitude is 25 meters per second and our theta is 22 degrees north of east. So for my vertical component, I'm going to go ahead and use my setup to get Vy is equal to V times sine theta. Plugging in those values, I'm going to get 25 meters per second times sine of 22 degrees. And that's going to give me a magnitude of 9.37 meters per second. Now, as the final component, I want to make sure that I check the vector, and I could see that Vy is pointing up, which is the positive direction. Therefore, Vy is positive 9.37 meters per second. Now, for the horizontal component, I'm going to do the same thing with cosine. I'm going to get that the magnitude of Vx is equal to 25 meters per second times cosine of 22 degrees. This will give me 23.18 meters per second. And I can look at the vector to see that Vx is moving to the right, which is a positive direction. Therefore, I'm going to say that it is equal to positive 23.18 meters per second. Now, when you're working on a problem like this, how do you check your work? Check your diagram. I can see that the magnitude of Vx is greater than the magnitude of Vy. So if my solutions are correct, that should also be true. And when we check it, 23.18 is in fact greater than 9.37. Now here's a spot where a lot of my students tend to get mixed up, which is when you draw an angle from the y-axis, your sine and your cosine are going to flip because you're not just rotating the reference angle, you're also adjusting that triangle, right? So if we look at sine and cosine now, for our vertical component, it's actually going to be adjacent, right? It is now touching the side where our reference angle is drawn. And so because of that, our horizontal component is actually opposite our reference angle theta. Therefore, it's going to be sine theta. And so when we solve for cosine this time, we're going to end up getting Vy is equal to V times cosine theta, while Vx is going to be equal to V times sine theta. And so in the case when an angle is drawn from the y-axis, we're actually going to see those trig identities swap places. Let's practice using this version. So in our case here, we're given that our magnitude is 49 meters per second and our angle is going to be 30 degrees east of south. So in this first case, I'm going to say that my vertical component is going to be equal to the magnitude 49 meters per second times cosine of 30 degrees. And that will give me an answer of 42.44 meters per second. Now I'm going to go look at my diagram and I can see Vy is pointing down, which is the negative direction. Therefore, my vector for Vy is going to be negative 42.44 meters per second. I'm going to go ahead and solve for my x component by multiplying the magnitude 49 times sine of 30 degrees. And this will give me a value of 24.5 meters per second. And looking at my vector, I can see it's pointing to the right again. So it's going to be a positive 24.5 meters per second. Once again, we can check our solutions by seeing that in this time, the magnitude of Vy should be greater than the magnitude of Vx. In this case, 24.5 meters per second is in fact less than 42.44. Now let's talk about how to solve for the magnitude. Let's say that you don't have an angle, but you do have at least two sides. You have at least two parts of the vector. So we can go back to what we learned in our math class about Pythagorean theorem and use it to calculate the missing component. The reason that we can do this is because the vector math creates a triangle. And in fact, it's a right triangle. So we can solve for C by going to add the other two components that are squared and then taking the square root. So for the magnitude of the vector, we're going to do that same exact thing. We're going to do Vx squared plus Vy squared and then square root that to get the magnitude of V. Now, because you know at least two sides, sometimes you'll be given the magnitude of the vector and you'll know Vx or Vy. Same thing, you just plug it into the equation where you find the difference between the total vector and the other component, those values squared, and then you want to square root it. Let's go ahead and practice this by looking at this example. Now we can see that we are given Vx negative 14 meters per second and Vy positive 24.25 meters per second. And we want to go ahead and figure out what is the magnitude of the total vector. So in this case here, I'm going to use that C setup where we're going to solve by adding the component squared. So that's going to be negative 14 meters per second squared plus 24.25 meters per second squared to get a total of 784 meters squared per second squared. At this point, I want to square root to just get V alone, and that's going to give me a final solution of positive 28 meters per second. So in this case, you can see that we use the other two components, the x and y, in order to solve for our hypotenuse. Now we actually are going to work backwards. We originally were using sine and cosine to find a missing length, but now we're going to use the inverse functions in order to find the angle. So in this case, we know that the inverse functions of sine, cosine, and tangent from our math classes. Let's look to see how this would work for a vector in physics. Inverse sine theta is going to be Vy over V. Inverse cosine is going to be Vx over V. And inverse tangent is going to be Vy over Vx. Now, you must be thinking, what's the difference if it's drawn from the y-axis? Well, the main difference is going to be that Vx and Vy are going to swap places, just like how they did when we were using sine and cosine earlier. Let's go ahead and do some examples. So in our first case, we can see an acceleration. We have the ax value and we have ay, and we don't know the magnitude of the acceleration, but we want to find theta. Well, if we have opposite and we have adjacent, we're going to want to use inverse tangent. So our inverse tangent statement is going to be ay divided by ax. In this case, that's going to be positive 4 meters per second squared divided by 3 meters per second squared. And I just want to let you know it's okay to have those units there because really what we're doing is creating a ratio. And so those units are going to cancel. We're really looking at 4/3. And that we can plug into our calculator to get a solution of 53.13 degrees. Now, let's look at it from the perspective of the y-axis. We can see that we're given Fx and the total magnitude of the force, F, but we don't have Fy. However, we want to solve for theta, so I can see we have opposite and I have hypotenuse, so I want to use inverse sine. So in this case, my inverse sine statement is going to be Fx divided by F. And that's going to be negative 12 newtons divided by 14 newtons. Once again, those units cancel, and it's just a ratio of negative 12 divided by 14. Now this will give us a statement of negative 59 degrees. Now you might be saying, what does the negative mean? Instead of drawing our reference angle to the right or counterclockwise, it actually means that we want to go the opposite direction, to go clockwise or to the left. I hope that this video really answers the questions that you have around what is a vector, how do I find the angle, how do I find the pieces, or how do I find that total vector. This should address everything that you could possibly need. However, if there are things that you would like me to address in a future video, please let me know in the comments section down below. Also, if you found this video helpful, I would love it if you like and subscribe and share this with your friends who are also taking physics with you. And I hope that you enjoy our new math segment. I will continue these videos so that way you feel confident when solving your physics problems.